So, today we're looking again into the time dilation. So let's consider again the next situation with the time dilation. We have spaceship, and we have Leo flying on this spaceship this way, and we have on the stationary planet we have his brother staying there. Yes, Nathan staying there. And they both have identical clocks, light clocks, where time measured when the light bounces between two mirrors. So get here, reflect, click, reflected back, click. So that's how they measure time. And clocks are identical. So when each of them look on his own clock, see this. And the time that you measure when you're looking on your clock, relative to which you are stationary to the clock. So you hold this clock in front of you, that's called proper time, T0. T0 will be proper time. That's the time that you measure on your own clock. But what happens when Nathan looking on Leo's clock? Because he's moving this way with the speed v, what Nathan will see that light going like this on the Leo's clock. Make sense? Now, by the time light gets from here to here, the spaceship moves this distance. So, and we take proper time, the time measured by Leo on his own clock. And that time will be T0. For that time, what Leo sees? When light going through this. So, light moving with the speed c. So, length of this will be c times T0. That's what Leo sees on his clock. The distance from here to here, speed, distance equals speed times time. The time measured by him. But what his brother observed? He looked on his clock, not talking, he's looking on Leo's clock. And for him, he measured the time, this is the speed with which spaceship moving, v, that will be the distance covered. That will be time measured by stationary person, measured time t, looking on Leo's clock. What this distance will be equal? C times t, because that time measured by the stationary observer. So this is c times T0, time measured by Leo. This time is measured by his brother. Let's apply now Pythagoras. We have that v squared t squared plus c squared T0 squared equal c squared t squared. Rearranging this for T0, we get T0 squared will be equal t squared minus v on c squared times t squared. And finally we get the T0 equals t times square root of 1 minus v on c squared. Now let's have a look on this thing. let's rearrange it, write it as gamma called Lorentz factor is 1 over square root of 1 minus b on c squared. Because v always smaller than c, what will be then 1 minus b on c squared will be always greater than z. It will be positive, but it will be less than 1. Yeah, it makes sense that 1 minus b on c squared is less than 1. So, gamma, when we divide 1 by something that less than 1, what we will get? We get more than 1. So gamma is always greater than 1. Gamma greater than 1. And rewriting this formula using gamma, why are we doing that? Why are we not leaving just in this form? Because this Lorentz factor will be coming up in many formulas. So it's useful just use this in this form. And we get that T0 will be equal T divided by gamma. Times by square root is same as divide by 1 over square root. Yes?
What is gamma?
Called Lorentz factor. And it's showing you, in this case, the ratio between the proper time and another time.
So this is the difference in time.
Yes, how many times one time? Ticking more faster than another. So which, let's say, gamma equal 2. Let's say gamma equal 2. By the way, let's find what should be the speed to have gamma equals 2. We have 1 over square root of 1 minus b on c squared equals 2. Rearranging this, rearranging this formula, we will get the square root of 1 minus v on c squared equals 1/2. Now we need to square both sides. So we get 1 minus v on c squared equals 1/4. So v on c squared equals 3/4. And v on c equals square root on 3 on 2. So speed with which you should be moving to have gamma equals 2 should be root 3 on 2 times c, which will be about 0.85 c. Makes sense how we have found the speed. Because you will have to do solving the problem. It's quite often you need to do manipulation with this formula to rearrange it. So for people who doesn't feel very confident with algebraic manipulation, it will be useful to have this formula rearranged on their cheat sheet. If you rearrange this formula for v ratio v to c, ratio v to c, this was gamma squared, so we get v on c in general, v on c squared will be equal 1 minus gamma squared. So v on c equals square root of 1 minus gamma squared. So put this formula on your cheat sheet. Or if you're confident with the algebraic manipulations, if you square both sides, yeah.
1 on gamma squared.
Yeah. Yes, of course. It is 1 on gamma squared. You see? It's useful to have this formula in your cheat sheet. So even if you can do algebraic manipulation, you can stuff up things. So -1 on gamma squared. So have it on your cheat sheet, because there will be question where you need to manipulate this formula. Now, so what we have, if gamma equal to, let me just step aside, find what the speed should be, about 0.85 of the speed of light. T0 equal T on 2. How we understand what does that mean? That for gamma equals 2, we get T0 equals T divided by 2. So, if for Leo, it passed 10 seconds. T0, 10 seconds. What will be T measured by his brother? 20 seconds. So time for Leo, time ticking slower, because he is moving. For his stationary brother, the time ticking faster. That's where we get in when someone went on the space trip, went to the stars, and someone left stationary on the Earth. The time for person who is moving, time ticking at slower rate. For time for someone who remains stationary, time ticking faster, so it will be more time. When you went to the star and returned back, it might be past 5 years for you. But for someone on the Earth, it could be 25 years or 50 years. Make sense? Now, how we approach questions. How we need to approach questions to solve equations with the time dilation. Let's consider on the example. Let's have a look on the page 15. No, not this one. Very classic. Let's do classical equation with the muons. Super classical equation. Page 38. Page 38. It's question 7 from 2006 exam. Muons are elementary particles created in the upper atmosphere by cosmic rays. And they are unstable, decay with a half-life. You remember what this half-life is?
Yes.
What is half-life? For half of them to decay. Yes. Half-life is the time over which half of your material decay. So their half-life is 2.2 microseconds. 2.2 microseconds. When measured at rest. So that means in their frame of reference, of muon's frame of reference, that will be their half-life. And there are 1,000 muons enter the atmosphere with a velocity of 0.995 c, and they pass top of the mountain of the height 2,627 meters. And experimenters saw number of the muons measured at the top of the mountain, and then the same beam of muons measured how many of them reached the ground level. And experimenters calculated the time that muon would take to travel from the top to the ground. And calculated value was much longer than the muon half-life. So experimenters expected, let's do the next thing. Divide 2020, let's say 2627 meters, divide by the speed 0.995 times 3 times 10 in the power of 8. Can you please divide using your calculators and tell me what will be the result?
0.000008.
So 8 times 10, can you please count zeros?
Negative 6.
Hmm?
6.
8 times 10 negative 6.
It's 8.8 times 10 negative.
Hmm? 8.8?
8.8.
Okay, 8.8. 8.8 times 10 negative 6 seconds. Now, 2.2 microseconds. In seconds, it is 2.2 micro remaining 10 negative 6. 2.2 times 10 negative 6 seconds. As you can see, the time for muons to pass from the top of the mountain to the bottom of the mountain is how many half-lives? 4. Every time, every half-life, the amount, the half decay. So as there are 4 half-lives, that means amount of the muon that reach the Earth should be how many times smaller? 16 times, 2 in the power of 4. 2 in the power of 4. So they expected that out of 1,000, there will be only 1,000 divided by 16 muons will reach, which is about 61, 62. Yeah. So let's say 62 muons will reach the ground. But they found that much more muons came through. How it is possible? How it is possible that they measured that much more? That means when they, from their point of view, their reference frame, their half-life is bigger. So to answer the question is, what is the half-life of muons measured by scientists? Yes?
Whose frame of reference is that one?
Now, this is what expected. What scientists expected, that if the half-life of the muon 2.2 microseconds, they moving with this speed, and this is the height of the mountain, so that's how long it will take muons to get from the top to the bottom of the mountain. So this is the 4 half-lives, so that means only 1/16 of original. There was measured 1,000 muons at the top, and was expected that about 62 will get to the bottom. But they found it's much more. Okay. Let's calculate what will be the half-life of muons in the scientist's frame of reference. Because that's what they expected. But much more came. Let's calculate what will be gamma. What will be gamma for this speed? Gamma is 1 over square root 1 minus 0.995 squared. Because when we divide this by c, c cancels out, and that will be approximately 10. Yes, that will be 10. Yes.
And how did you get that, sir?
Huh?
How did you get the original equation?
This equation, gamma, formula for Lorentz vector, square root of 1 minus v on c squared, and v divided by c, this is v,
Okay.
divided by c, c cancels out. So gamma equal 10. So we have that in muons frame of reference, when muons measure time for themselves, their half-life is 2.2 microseconds. But in the scientist's point of view, they are stationary. The time will be dilated by gamma. So it will be 10 times 2.2 times 10 negative 6. So it will be equal 22 microseconds. So for them, the time half-life will be much longer. That's why more muons came, they observed more muons. So solving the problems with the time dilation, you always need to decide who is moving, who is stationary. Who is moving, who is stationary. And person who is moving, or person or object who is moving, measure proper time. Proper time measured. So proper time measured by yourself, for yourself. So if moving object or person move time for him, her, itself, that is a proper time. And if someone who is stationary and measure time for moving object or person, that will be dilated time multiplied by gamma. Yes?
Does that mean that the 62.5 was in the frame of reference of the muons?
No, this was, no.
No, the number doesn't change, that's just what they're saying would be.
No, that's what was expected.
But isn't that in the frame of reference of the muons?
But for muons, this distance will be smaller. We'll learn about this, not for the muons. That's what was expected if time will tick with the same rate for moving muons and stationary muons. That's what would be expected. But in reality, because their time, half-life becomes 22 microseconds from the stationary observer point of view, which is much longer than it was before, and so this will be even not a one half-life. So much more muon will be able to get through. So again, steps to solve problems with the time dilation. Identify who is moving, who is stationary. Who measured time for itself, and who measured time for someone else. Let's look on another example where we need to do this. Okay, let's open our booklet on the page. On the page 15. Page 15, we have question number 11 from 2020 physics exam. An astronaut left Earth and traveling on a spaceship at 0.8 C and gamma, thank you, already calculated, don't need to do that. Page 50, it's question 11 from 2020 exam. We have speed equal 0.800 C. And gamma already calculated equal 1.67. Traveling directly toward the star known as Sirius, which is located 8.61 light years from Earth, as measured by observer on Earth. Now, what is light year? Remember what is light year? It's not a time.
Distance.
It's a distance. Light year is a distance that light traveled in 1 year. It's a distance. So, if the distance is 8.61 light years, that means it takes light to travel from Sirius to Earth 8.61 years. Now, how long will the trip take according to a clock that astronaut is carrying on his spaceship. So show your working. Now, as it has distance measured by scientists 8.61 light years, how long it will take from the point of view of the observer on Earth, how long it will take it to move spaceship to get to the.
Is there a question from a clock that is carrying on spaceship?
We need to do
Isn't it 8.61
8 point.
0.9?
We need
What's
multi.
the other way?
Will it take, because it's moving not at the speed of light, it take 8.61 years if it's a light. If it's a light with the speed of light. Now,
Is there not a conversion from light years? Is there not a conversion from light years to like normal stuff?
no, but
Could you do light years divided?
Yeah, it's
Just
divide,
meters.
it's divide.
so we need to, because spaceship moving slower than light, will it take it less or more time to get the
More.
8? More. How we find that? We need divide 8.61 divide by 0.8.
Why?
Because 8.61 is how long will take light. But this moving slower than light. So it takes more time.
So it's 10.7 years.
So that is equal 12.35 years.
12.
12 point.
10.7.
Hmm?
10.7.
10.7.
What? Sorry, my bad.
Click the next one.
Sorry,
76.
10.76 years.
Years.
Years to get there. Now,
Yes.
Wait, why do you divide it by 0.8?
Because
Distance equals time equals distance over speed.
it's not 1. If it was 1, that would be the amount of years. But it's 0.8.
okay, let's approach it a little bit in a different way to make it more clear. What? Why have different number here? 2020.
It's the other way.
So,
It's why I
T0 equals T of the length.
no, so 86 point,
But see now, like you meant.
yeah, 8.61 divided by
okay, it's like
0.8. Can you please remind 10 point,
7.6.
Like
10 point
7.6.
76?
Actually,
That is how many years? That is
surely.
how many years will take a spaceship to travel from whose point of view?
Spaceship's point of
Yes.
From Earth point of view. From Earth point of view. Because we have just, we divide distance over speed to get time. This is distance, this is speed.
view. Yeah.
Distance over speed, and this distance measured by Earth, so this distance is stationary. How long it will take from the astronauts, how long it will take?
8.61.
We need to divide
Divide 10.76
10.76
by Lorentz.
How
divide
do you know
by
Because
T equals
1.67.
simple transform.
T.
6.44. Yes.
Wait, so because
Yeah, why does it say in that? It says 12 points.
Damn, that's confusing.
so because you're measuring,
Fucking
how do you know the first one was from Thingo?
Hmm?
How do you know that the first one was in Earth?
I think that'd be rather than to like.
Okay, let's consider another example. Maybe we'll make it more clear. We have distance is 10.5 light years to the star. 10.5 light years.
Question doesn't know.
measured by Earth. Spaceship travel 0.85 C,
Where are we?
which gives gamma equal 1.
Page before.
Okay, thanks.
Gamma equal 1.9.
Yeah.
So, how long it will take in Earth frame of reference for this spaceship to get to the star?
10.5 and 0.8.
We need divide 10.5 by the speed in light relative to the in speed of light,
12.3.
12.35.
Yeah.
12.35. Does that make sense? This is time measured by observer on Earth. Because it's just distance measured by the observer from Earth, 10.5 light years, divide by the speed, distance divided by speed, we get that much. But this is a proper time or dilated time?
Dilated time.
A dilated time. Why it's not a proper time?
Proper
It's
time
measured
from
from
the
Earth.
spaceship.
Proper time will be from point of view who is moving. So when spaceship is moving, the time measured by the spaceship, we need to divide this
60
time
years.
by the gamma. 12.35 divided by gamma, and it equals 6.5 years. So from the point of view of the person on the spaceship, it takes 6.5 years to get to that star. Because we identified who is moving. Spaceship. If spaceship measured time for itself, it is a proper time. And proper time always shortest time. Make a note. Proper time always shortest time. From the Earth point of view, it will take longer. Dilated time will take 12.35 years. Yes, it's a question.
So if anything in the equation is measured by the stationary observer, it's not proper time.
For who? Depends for who it's measured.
By the station.
If you measure, no, question is, I will measure for yourself, everything that you measure for yourself
Okay.
will be proper time. But in this case, we have spaceship moving. So time for how long it takes spaceship to get from here to here, proper time can be measured only by spaceship. For stationary observer, it will be longer. So always identify who is moving. Proper time is measured by the moving object. And it always will be the shortest time. For another observer, it will be dilated time, it will be longer. Make sense how to approach those questions. Okay, like, subscribe and donate. Support Ukraine and Israel.